like machine learning or deep learning or data analytics or any sort of modeling for better visualizations. So certain areas of where AI and machine learning are already being applied in sports. Not only in sports, there are also some other human activities where we can apply this AI. So these are the few topics we have already discussed, like making a strong decision by making fusion kind of or combining decisions from several predictors, and finally we may take the decision whether the player is out or it's a six or there is a no ball. So that kind of thing can be taken out by the using AI tools. And one more important thing is nowadays people are very much using the different wearable technologies like smartwatch or some body attached sensor in our foods or in our in other parts, which will basically collect lots of our sensor data in terms of signals or waves, as well as biometrics are also taking like gait signal, heartbeat, or some sort of DNA. So those are useful for recognizing or authenticating the player is really genuine, or any such of doping or any inherent or in body particles which are influencing their performance all can be analyzed. So these are really very fantastic tools nowadays coming in the area of the scores. Now, so it is now clear for to us that all of these are very much important. Now, what is the role of computer vision in this area? So computer vision or AI both together are combining with these machine learning techniques, and there are several different applications are building. So here we are deriving some key points in the body of the player. So key points basically gives us the joint points of some specific part of the body, like in shoulder or in finger, and based on which we can use some sort of pose estimation. So pose estimation is one such important area which is widely used through the computer vision techniques. And based on this pose, the of the athletes or gymnasts be analyzed, and accordingly the some points will be credited. So in that way, there are different types of estimator pose estimations techniques are available, which can be applied in sports, in yoga practice, whenever you are applying online teaching for yoga assistance. So you will, in real time your video will appear, and then some joint and the angular measurement will be taken, and based on that how much your pose is erroneous with respect to the standard pose of that particular yoga or asana. So that is also a very important area for the pose estimation in computer vision. And another one is the dance. So dance is also again some sort of body exercise, and these sports or yoga or dance all are required in our day-to-day life for very good health and well-being. So these are few examples where different types of activities are going on, and we are measuring the body language, whether there will be foul or some offside. Based on these key points, we may analyze the performance of the sports. So few examples has taken from the online resources. Now, how this pose estimation or can be applied to measure the pose. Suppose I will upload an image to an online pose estimator, and based on that image, the tool will provide me where are the key points of that or within the given image. Like one, there are several pose estimator. One is very popular, which is open pose. So it can take real time pose estimation by selecting the key points. So it can select different body joint points or some key joints in our hands or in face also. These are very much efficiently or correctly localize the different points, which cannot be detected by the human eyes in a realistic or in a bare naked or open eyes. We cannot see these joints point in our open eyes whenever particular the person is having the clothes on over the body. So that's why this is very important for analyzing the critical analysis. So in this diagram, all these points are located at different body joints, and accordingly there are 15 or 18 or 27 key points can be localized, and based on that we can get the key points. Now how we will take these key points? So accordingly of these coordinates, so these if we plot in Cartesian plane, we may get some such sort of features, like what is the angle between this point 4 to point 6. Some distance will be calculated with other points. Accordingly the pose is how much correct, that can be measured, and accordingly the gymnastic will give him some points. So in hand or full, all over the body, this is important. So other than open pose, there is also another is called alpha pose and media pipe, which are also object, I mean pose detector from the skeleton image. So these are also used in dance for video analysis. Another one important area is the object detection. Like in this example, you might see in case of swimming, every player is surrounded with some rectangle which we call as a bounding box to denote his positions. Because in water sports, it is very difficult for a human to analyze, because the background or environment is very much noisy, and it is distorted of occlusion due to the different uh, uh, marker as well as the water flow during the swimming. So therefore, we need some sort of high-end camera, underwater camera, as well as some top view, by which we can surround the area of that sports person. Also in football, we might detect the object, like here the football is there, we may add some bounding box and the player, whether some foul is taking place or any such motion analysis. And there are different types of object detector tool presently available, which will detect not only the person or the object within that image, they will also provide some sort of label of the object. That means what is the object is. So that can also suitable for classifying the object. So they can classify this as a ball, this as a person. So including the object detection or localize where the object is, they are also suitable for classification of the object categories. That is also important. So this is also having a volleyball competition. So there are different types of object detectors are nowadays available freely and which are very fast. Other than object detection, we have another task which we call as a semantic segmentation. So this is basically to find out and categorize the different object into different category. Like in this case, the person who is cycling, he is one category of object having a different color, as well as he is riding a bicycle, that is a different kind of object, so that is in a different color. So accordingly, all other athletes or cyclists are colored accordingly. So this is called the segmentation of the region of interest where the object is lies, and categorize or assign a particular color or label to discriminate between the other object, as well as it gives some sort of context information. What is the context information? Basically the surround information, which will useful to generalize the object in a single category. Though this person has a very different body color or some dress like white, then yellow, and some helmets, but altogether it is segmented in a single object. So based on the context or surround information, semantic segmentation is useful in different applications in not only sports but in automotive or driving, and medical segmentation where like it's a cancer image where the cancer cell is being actually infected. Those are suitable for segmenting the regions. So now, what are the different object detector that we can apply in our work? So basically, there are two types of object detector tool available. One we can say as a one stage or single stage. Another one is stage or region proposer. So this is the example of one such two-stage where two different network is included to get the region proposal. Region is here basically that bounding box, which we can even as a bounding box have some starting coordinates x and y, and the height. This is the width and this is the height of that box, so that we will get the exact location of that person. So once we have an input image, then we will apply some CNN layers, convolution neural network layers, or deep learning model to identify what are the important features are there in that image. And then there will be another network which we call as the RPN, region proposal network, that is useful to detect those different bounding box of the objects. And finally, both of this image and this image will be combined to localize the overall object with the surrounded bounding box. So in the previous example here, you can see all the objects are surrounded with the bounding box from the given input image. So this is basically uh, either we can use in a double stage or two stage by a faster RCNN or region based proposals for detecting the object. So it will have some length and width, which is a combination of both of the networks. Another one is the YOLO. So YOLO means you only look at once. So this is very faster because you have to just process in a single stage. In that category of object detector, this region proposal framework is not available. It just localize those information and applying that, it just get the bounding box of the informations. So that's why once we analyze this YOLO, these are having very low complexity and very fast than the other, because in RCNN families, these are the slightly improvement over the years. So RCNN starts from Google Net, or a very old or previous or earlier CNN architecture, and over the years that has been improved to get more speed into it, because this is a two stage, so therefore some speed will be lagging, and over the years they are improved, and finally they have also devised the mask RCNN. So this is another kind of RCNN for object detection. Likewise, YOLO has several variations. So right now we might have YOLO 5 to YOLO 8, we might have the recent one. So YOLO 1, YOLO 2, basically these are also using some sort of uh, network which like called darknet. Initially YOLO was on darknet. Recently it is also using some efficient net architecture. So all of these are different types of CNN. So I'm coming into what is CNN after this discussion. And we can see also some sort of comparison about the different region proposals or object detection. Now, in case of the sports, we might need some faster, so that once the athlete is running at every frame within 50 or 60 frame per second, the image should be captured and respective bounding box will be provided, such that we can capture the latest or the most prominent informations. So in those cases, we might prefer YOLO, but in some other applications where we need to generate some sort of mask, then this RCNN is applicable. So there are lots of research work is going on using both of the object detector, using YOLO as well as the RCNN families. And next one is the semantic segmentation. What we have done, just how it works. So basically, semantic segmentation is dividing the image based on the context of the input image into couple of or few number of categories. Like if you see this diagram, you can see this image has been divided into one, two, three, and four different categories. But the building, road, and car are being shown. So these are segmented into four different objects. How this is being done? So we have a an encoder. So this part is called the encoder, and this part is decoder. So these are basically a kind of CNN architecture combining different layers. So initially this is slow, removing or squeezing the size of the image into a lower dimension of some feature space. So that's why the size of the image is shrinking to the encoder. After that, it will have some latent space where some feature will be there, and then again it will be increased to that original dimension of the input image, such that both input and output can be combined together to have the same dimension of the image with the segmented region. Okay, so here the task is we have to classify the object, that means how many objects are there, and then localize where the object is actually being present in that image. So using that object detector or bounding box, we may get the information. And then segment means group the similar pixel into a single category or one category. If there are some other car, so that car will be completely different than the background road. So it will be clubbed together using some segmented region by the grouping of pixels. Now here if you see in this top diagram how this segmentation is being taken place. So we have some input image, and input image is basically we can say as a RGB image. So it has three color channel RGB, and the height of the image is say H into W into 3. So where these three basically these color channels. And then from this input image, if we apply this encoder decoder architecture, we might get some information of different regions based on the category of the object. So if we have this one, that means that is the human object. Then the background object or the surround object is denoted as, there is also another object which is the bench is another object and 3. So now there is also another object is 4. So 4 is here basically a cat. So these 4 different regions or different types of objects are there which are being segmented. Now each of these different objects have some same dimension as a mask. So these are the masks for respective objects. So if we consider the person object, then it has marks only where the 1 will appear, and 0 is basically the black pixels. Okay, so if we now superimpose with this with the input image, then only the person will be visible. The entire background will be dark. Similarly, if we use the next one for the bench, then the plants of the background and the cat. So if we now combine all 4 masks into a single, then we might get the segmented image of this given overall input image. So this is also applied to this segmented image, in this case which is the road. So we have 4 regions like the car, then the building and the road and some complex other part. So all are combined together to have a segmented region. So all of these are very important in the applying for any sort of applications. So the main applications are like the object detection, classification, object classification, object localization, segmentation, which all are important to apply in the field of sports, because these are the classical computer vision techniques, algorithms which are applied different applications areas. Okay, now how, so and also for analyzing the sports we need some sort of information in terms of image or video or some signals. So which kind of sensor that are useful or being used in sports? One will be the camera, high resolution camera, which are placed the side or in different area of the where the performance is going on. for athletes, for jumping, for running everywhere. And then we also use this camera. So these are the visual camera or high resolution DSLR. So this is called as a thermal camera. So it also takes the body temperature. Body temperature of the person will take place. So one example is shown here. So this is also useful in night vision or very uh, cloudy or adverse weather condition where this normal camera will not work. This thermal camera will give us that information about the surround temperature and the context of different things. So some applications, this thermal camera is also useful, and particularly for the sports persons injury analysis, this is more important because it also gives some sort of thermal information. And then we might also use some sort of wearable sensor and wearable device, so like the smartwatch or some sensor in the sports shoes or in some hat or in some chest. Those will take some uh, electromagnetic signals or audio signals or some sort of magnetic resonance signals. Based on that, we will apply some uh, deep learning or machine learning algorithm and analyze which part of the sports person is more involved in that taking decision or performing the sports, or if any of the organ is being injured, those signals will give that kind of information. So uh, these signals you might have seen in case of cricket where the player is having a chance of a out for the wicketkeeper where the bat is slightly touching the ball and some sort of signals or noise will appear. So those kind of signal or sensors are very much important in any kind of sports for more better predictive analysis, whether it is really out or it's a just a background noise happening in the field. So with these different kind of sensor and wearable devices, we can take some sort of data from the sports person. Now, so now I will move into some elementary work that we have done, and if you have any doubt, you can ask me. So far, whatever we have discussed about these basic things, then we can move to the next part. So, any question, or we can move?
So I don't think we have any questions yet.
Okay, okay. Okay.
Yes, yes.
So now, based on these few the basic computer vision tools, we have done some sort of image processing applications. So our work is called SID. So the name comes from the sports and yoga and dance, which are similar body pose estimation problem, and it involves very complex body parts. So this is the task of classification of the. So basically, this is image classification task. That means, uh, so as you have seen in the previous slides, whether we are using some object detector or segmenting segmentations or semantic segmentation or the localization part, we need first what is the object is. Likewise, in sports, we might have to see what the sports activity is actually going on, whether it's a javelin throwing or a cricket or it's a tennis or something. So this classification is very much important. So before this, there was no public data set of large scale having considered hundred of more sports activities in a single data set. As you have seen, for analyzing, we need the data set is the foremost important input. So we have to first generate or create some data. So therefore, we have collected some data from the public repositories in Kaggle. So if people are working on any sort of image processing or computer vision work, you might heard about the Kaggle is a freely accessible data repository where people can download any sort of data which are available, and you can start your own work. As well as you can also fix or collect the images from Google, Bing, Yahoo. There are lots of other websites where public images are available. Okay, so from this we have collected one is some sports 102 data sets and the dance style. So we have more samples in the dance. For this, we might have not that much of good dance data set available, which combines both the classical like Bharatanatyam, Odissi, and some of our folk dance. So folk dance is also nowadays included in the UNESCO heritage sites like Chon or Bihu or the Dhunuchi. So these are the different folk dance of our West Bengal, as well as this is a dance from Rajasthan. This is Odissi. So we have combined 12 such different national and international dance posture for classifying the poses. So this is the overall image level description, that the x-axis we are giving or showing different data level to each of the action, and y-axis level we are giving the how many samples are there. And then for image processing, or sorry, for image classification, we need to define two different thing. One is train set, another one is test set. So this red color is used for training and the green color is for testing. So generally standard way is to use 17:30 ratio to train a model, and then the test what is the accuracy or the performance of the model. So model is here basically a CNN model, convolution neural network, that I am coming afterward. And similarly, we have the DAMS dataset having 12 classes having around more than 500 images per class, both for train and test ratios. These are those DAMS forms. And then after collecting the data, we need some data cleaning, because the data might have some wrong information uh, or some noise or some mislabel. That means if a image you may find which is basically should be a cricket, but it is given inside the football. So that for data cleaning, authenticity of the data set is very important. So once we have downloaded the yoga data set from some researcher, we have found some noisy or wrong images are there, like these kind of fake images are there. We have to clean or remove so that our data set should be more reliable for analysis. So if your data is not good enough, you cannot analyze your model, or the algorithm is performing well, or there is some issue with the data set. So that's why before starting any sort of experimentation, we should think about the data stage or data processing part. After this, some that was dance 12, and recently some of our student has increased the data set by adding more 8 more new dance poses inside it. So now our data set is increased up to 20 categories of the different dance pose styles, as well as the 100 to sports. So now we have two different data sets to perform or analyze our model. Now, how a model can be developed? So, are you familiar with, or have you heard of the deep learning or CNN from the audience? What is CNN? How a network is being made?
So the participants may have heard these terms, but they're not familiar with the details or specifics about these terms.
Okay.
Yes.
So, convolution neural network is basically involves some convolution. Convolution is some operation between some two windows, like say this is our input image of this size, say this is 224 into 224 into 3 is for RGB channel, and then we apply some sort of filters. Filter is basically some values in a window in a 3 to 3 grid have some random values 101 or 102 and like. Now in your input image have this much information like 111, 1010, 111. Then multiply this information of the image with the information of the filters. Then you will get some result in form of sum. Like this 1 that is 1. Then this 01 is 0. So 1 again 1. So plus 1. Then again 1. So this is 1. And say this is also 110. So again 2. So these results of this first column will be 5. So the feature which we call feature basically the characteristics or attribute of some pixel positions. So once we apply some convolution within this image, then some information will be extracted from the raw image. And at every layer or every more block, this information is transforming into a different representations by using the convolution. So that's why it is called a convolution. And here the layers are multiple layers. There is no not only one or two layers, there are hundreds of layers will be there. And each of the layer is connected or consists of some sort of neurons. So these neurons are basically those part of network. It might be activated or deactivated based on some threshold values. Now suppose here this information is available. I applied some convolution. Now whether that information will be propagated to the next layer or not, that depends on the activation functions. So basically at every layer the convolution has three main part. One is the convolution which we denote as a conv. Then the pooling. Pooling means extracting that information for the next level, as well as it will squeeze the size. And then the activation, by which activation that information will be propagated. Afterward, at each layer, you might also apply some regularization to regularize by covariance sheet of the information in a single layer. So these are important. Now, for this layer, traditional neural network has limited layer, but in deep learning, as we call as a deep, so there are deep to deeper levels. So several hundreds of layers will be there, and each layer we are applying the convolutions with these are the filter sizes. So 32 into 32 filters will be applied in the first layer, and then we are applying some pooling layer. Pooling is to reduce the space. Like say here we have this much information 1, 10, 8, 5, 20. Now if I apply the max pooling, that means from this feature map that you have derived, which will be the maximum, the 20. So 20 will be propagated for the next level. Or if we take another one, there is basically two different types of pooling. One is called max, another one is average. Then if we take the average pooling, then the average of this information will be propagated. So in our network, we have applied some convolution with these size. At every layer, we are increasing the size of the channels. Okay, that is the convolution. As well as this pooling basically reduce the size. So the size of the input is gradually lowering down towards the end of the network. Okay, and then each of the information is activated by some activation function which we call as a linear activation, rectified linear. So basically it takes the maximum between 0 and the maximum value for this one. So if it is 0 or 20, so max is 20, so that will take it. So here only the positive values will be propagated. So after towards the end, we might have the feature size like say 7 into here it is 1024. So the feature space will be 7 multiplied with 7 into 1024. Okay, then we flatten that. What is this flatten? So now this is a three-dimensional feature space. We will flat into a single dimensional vector. So the total information will be this much. 49 into 1024, and then it will pass through some dense layer or fully connected layer. So now suppose if you have a three-dimensional space, now you have a single dimensional vector like this, and then we add some dense layer with few number of neurons and connected to each other. Okay, and there will be the final layer which we call as a softmax layer. Softmax layer, that is basically gives us the class probability. So now if we have only 10 number of classes, so from this dense layer it will select the probability of the each of the class. That means whether this dance pose is for which one, Bharatanatyam, Kathakali or Odissi or something. So if in our data set has 20 different classes, for each of the classes it will predict some probability, and based on the highest probability we will classify this image belongs to that category. So this is a very general architecture of any CNN architecture. And if you want to get some more information about this, we can show you the Kaggle repository is there. That is another example which we can discuss afterward. So this is how a general CNN works. So we have to apply some convolution, then pull the feature or extract the feature which are important, and then pass through some flattened layer or dense layer, and finally classify the level of the class. Now our student has applied this data set, and then during the training they got, so training is the term for when we start the experimentation and run few epochs to train our model is doing or learning correctly or not. So in the learning curve you might see first the term is accuracy in the x-axis, y-axis, which is gradually improving from maybe 40% up to 90%. That means our model is learning something from the given input of data. But during the testing, we might see it is starting with high level, but the gap is still training and test is something more. So this is a normal behavior of the curve because training accuracy is generally always high than the unknown sample which you are using for the validating your model. But it should be as close. That means your model will be much more better. So this also gives some cause of term called say overfitting. Like if your model is performing well on a known data, but when you give some unknown data, it may uh, not get that much of accuracy. That's it. So that means your trained model is very good, but your test performance is very good. So that's why we have to regularize the model as well as generalize the model so that it can do on different data set as well. Now, why we have chosen both of the dance as well as sports? Like say, if I train my model on dance, so dance is giving good, but when I change the data set to some sports, then your performance may degrade. So I cannot claim my model is good enough to generalize any kind of sports action. So that's why you need to experiment on multiple data sets for a single model. So accordingly, we have different CNN architecture like here PGG, mobile net, inception, and our own model. And each of the model will have some different learning curve. Okay, so accordingly, we may analyze which model gives us the better performance. So in this case, these are few numbers just for sake of understanding. So in this case, you might see uh, mobile net performance better than the some other networks. Now here two terms we may also learn. There is no augmentation. Another one is augmentation. What is that? Now this is also a part of developing a model which will influence more variability in the input data set. The CNN is very smarter than the human. That's why AI is more useful and giving more better analysis than the human. Because I said this is an input image. So in computer graphics, we have heard about some terms like rotation, translation, scaling, sharing, and so many things. So these are basically different sort of transformation techniques. So these are used to distort the image into different angles. So if I apply some rotation, then this image will turn into like this. I mean applying some sort of rotation with respect to its axis. Or if I zoom it, then it will magnify. If I crop it, then it will reduce. So this basically gives or change the pixel position from x y to x dash y. So if it is x dash y, it might be x double dash y and y double dash. So basically changing the spatial location of the information. But even if I rotate the image, the context of the image or the content of the image cannot be misinterpreted, because we can also interpret a rotated image whether there is some human or there is some cat or dog or any other object can be identified by the human vision. Likewise, the CNN can also behave the same. That means it can localize object in translation invariant manner. That means the object might appear anywhere in the image. It may select or it may very easily can interpret where the object is. So that's why if we add some variation in the inputs, then our model will learn better and reduce the overfit. So and reduce the overfit. So therefore, lots of different sort of augmentation techniques can be applied. So these are the classical or well-known things like rotation translation. There are some new thing we also added, which we can call as a cropping. So from that input image, I have cropped the central part. This is called cropping. And if I pass this one, our model will learn only this most important region other than the surrounding information. So it may easily find out what the pose of these dancers are. Another one we can call, here you can see some part has been erased by some gray pixels. So this is called random erasing. That means I am erasing the actual content randomly by localizing or pointing some area and remove that part from the context. Like in quiz or puzzle, we might have seen this kind of thing. And this is not only gray color, it can be of different size. Here we have only a large rectangle where we can segregate into different rectangle with different color. It will give more chances to learn in short regions, or we can divide the entire image into very small regions, which we can call as a patches. So the entire image, this one, is divided into small patches, 1, 2, 3, 4, like that. Okay. So these are called patches or small regions. So basically what will happen, then the model will localize or see which in regions are important. Like in case of the object localization, when we use the YOLO or marks are seen in this kind of architecture they have followed to interpret where the object is. So that's why we can use this random augmentation also. Okay. So then we can also extract the bounding box. So these bounding box are giving in random. So if I apply different execution, the rectangle positions are of at different locations. You see all images are different. So when the epoch starts, the same image can be interpreted first with this epoch in epoch 1, or in epoch 2 it may change to this, and in epoch 4 this, or epoch 5 this. So at every epoch or at every iteration, the model has a new kind of sample without changing the content but removing some part of the information. And then we see whether the model is really doing well or is baffled as the some results are off. So this random erasing information is important for getting more insight into the model. Now this is the overall model architecture. It's little complex. So I have, so this part we have already understood, that how the image is there. Then we have applied the base CNN. Base CNN is that CNN architecture that we have discussed here. So this is one kind of CNN architecture which is added in the network, multiple layers. And then also we have seen the in the previous slide how the augmentations are applied to generate the patches. So up to this it is fine. And the remaining part, this classification is also we have done. Now we have also only this part, how this part is applicable in the model. So here we can only understand this is called the attention. So a more simplified diagram will be like this for us to understand very quickly. So this is the input image. With the augmentation, we have applied this backbone and then classification. And in between the backbone, we have injected two more layer. So these are called the attention layer. So why this or what are the use of these layers? So once we have some sort of attention, that means the model will focus where the most information, like in a normal image. Once we have some image and we have to identify where the region of interest is there. So this attention basically focus only the information which is required and ignore the other part. And these are also useful for long range dependence. So these are very important term, long range dependency. That means generally if the object is here, one part of it, so we assume that the nearby area is for this object. But sometimes it may also happen some context of the same object will appear in a different location. So it is able to localize those two different regions which are far apart in the image plane and make some relation. And then it identifies this is the information which we need to learn. And accordingly, we may give some weight that what are the different objects. Like if I see this diagram, so we might see this hand is at this region and the other hand is in this region. So we can identify this is important part, this was also important. So our model will localize or information will be focused only this region where these other regions which are irrelevant will be discarded. That means the activations of the neurons for this will not be much. They will only focus or pass the information only these informative regions in the further part of the layer. So that is being formed in the other one. So we have two different type of attention. One is spatial, which is applied on the dimension, height and width. Another one is channel, which is applied on the channel space. So once we have a feature map is of this dimension. So this is the spatial, that is the size of the image, height and width. In this direction, another one is the channel. Channel is that RGB, we have seen 3, but now we have 1024. So these are the different channel dimensions. Every one has a 1024 feature space. So this becomes a very high number of features. And then from that it will select. Afterward, we might have some results, and we have seen more number of regions is giving better performance than some other regions. So here we have got with 30 regions better results than some other network. Now, how we can assess the performance? The performance can be assessed using accuracy, precision, recall, and confusion matrix. So in the right side, you might see this is called the confusion matrix. So how it works? So diagonally, it will gives us the best performance, which basically one is the true class level, another one is the predicted class level. So this is the true and predicted. That means this is correct. That means with this much information, we may analyze the result. Now, also we can visualize the model performance in some feature analysis. Like the top row is showing like some grad cam, we can say gradient activation. Now you can see this is some attention map where the most important region of every image is being shaded and shaded with the red color, and the other part is being. So the attention only focus the informative regions. This is one kind of visualization of the model performance. The another one we can call as a TSNE, stochastic nearest embedding, node embedding. So if you see, initially we have this much where all the information are clubbed together, and afterwards they are segregated into different colors, and finally they are into different regions or different segments. What is this? Now, once at the initially we have all the features are clubbed together, we cannot discriminate. So this color is basically those different objects if we think about the segmentations. So similar points having higher probability having a single color, and then if we apply some sort of attention, then the density of blue color is towards the right side where the density of the other colors are different. Then again, if we add more few layers, then all the different colors are segregated with that much of sun. So these are different, notifying the class. What are the class? Like whether the dance is or the sports is cricket or this is a football, or this is volley, other one. So you can segregate the feature level representation also using the CNN. Uh, the next work we have like so far we have generalized only the sports data set for the both male and female. Now, after studying few literature, we have found there is no specific data set for the women. So we have nowadays we have so many women athletes and they are performing very well in the Olympics and everywhere. So therefore, we have created one data set with only of 50 different actions. And again, we have developed similar kind of data distribution and some model using those different regions and get some elementary result on that data set. So here we can see our DenseNet is performing good than the other neighbor. And the respective confusion matrix. So as you have said, the actual levels are in this side. These all blocks are class level. These are the predicted level. And according to this, where the two positive or two negatives are there, that is what with the principal diagram. This is for assessing your model's performance. After CNN, we have also integrated another kind of network that is called graph convolution network or GCN that can be also combined with the CNN to get some better result in the architecture. So as you know, in graph data structure we might have learned graph. Graphs are represented in terms of nodes and nodes are connected with some edges, and then we can also represent some adjacency matrix to find out the relations between edges and the nodes. Similarly, this image is nothing but a graph where each node can be represented by some pixel values and make some relation by if they are neighboring or connected by some adjacency matrix. So after applying the only CNN or normal convolution, we can apply the graph layer on the top of it, apply the pooling technique, and then the classification. We will also design a new kind of network architecture. Again, we have got some results on this. So these are the different work that you can also start or you can try for learning some sports action classification or some sort of localizations or segmentations. Now, so I'm now going to conclude the session. So what is the future of sports? So the AI just started its journey in sports, so it has to several new revolution will come in the coming years. So apart from decision making, it will also playing some crucial roles in injury prevention, or optimal conditions or estimating the chances of probability for winning the games. And there are also some online games also nowadays people are playing online in IPL. Here the AI is giving the winning for the next 20 years. So it can envisage what will be the outcome of the next 20 years. It is just for a vague idea. That means it can go beyond couple of years, can predict something based on the data. But if the data are not good enough, then the prediction will be wrong. So one more limitation of the deep learning is it is data hungry. That means as much as data, better good quality data you will provide, you will get better results. Like in weather prediction also, you might see if you give some wrong weather input data, you will get wrong prediction for whether today will be raining or not, this kind of things. So we need good quality of sensors, good quality of imaging devices so that you can predict the difference between fractions of millisecond in 100-meter run or in pose estimation in javelin. Good quality for in sensing devices. And the contribution from our side is that we have generated few new data sets and then we have applied some data planning model and get some state of the art performances, publish the papers. That's it, our conclusion. And we are also thinking to do something more which will be really practical and applicable for the sports athletes in the context. Because in India, uh, we need we are lacking that much of funding from the sports. So if we produce some low cost sensor or low cost solution for our players, then it will be beneficial for our country also and uh, middle class or poor class countries, because we are not spending so much of fund like US or Europe in sports. So that's why our performance also very less, as well as we are not getting enough sponsor from the government side. So we need to encourage the motivation for industries, startups, and companies to engage more research oriented activities should be performed in the coming years. And these are the references and the data set which we have done is available in Mendeley. You can collect and you can start with for your work. And thanks both of the colleges for having this discussion on the sports. Thank you.
Thank you so much, sir. If you have any questions, you can raise here. Sir, I think neural networks have threatened our participants.
Okay, so we can conclude, or is there any question or any research directions that you need to know? So not right now. If you have in future, if you have some sort of queries, you feel
Yeah, I
freely.
will let you know, sir. Yes. Okay, okay. So, thank you, Dr. Bera, for this interesting presentation. So initially I was wondering how this presentation would unfold, but after the presentation, I realized that I've seen those videos that you showed on the slides, but failed to aptly appreciate the machine intelligence involved. Thank you for making us understand and appreciate how AI has revolutionized the world of sports and is being constantly in business, as you said, in the training process for the players and athletes around the globe.
Yes.
Yes, yes. So thank you so much for this interesting presentation. We all can at least comprehend that AI to work, we need huge volumes of data. And at this day and age, it has become possible to integrate AI because of the computational capability that we have. And as you rightly said, the technology or the sensing devices that we have, which have helped us integrate AI into all aspects of our lives, actually. So thank you so much, sir, once again. Thank you for this wonderful presentation. And I would also like to thank my co-host, Dr. Sushmita Lama, for hosting this webinar. Thank you so much. Thank you to all the participants. Thank you so much.
Thank you, sir.
Okay, thank you. Bye.
যারা আছেন আমি একটু আপনাদের সাথে এটা শেয়ার করে দিই ফিডব্যাক লিঙ্কটা ওকে জাস্ট ওকে ঠিক আছে থ্যাংক ইউ সো মাচ